going live. And we are live. Hello, everyone, and welcome to the Gravity Max live stream. Today is January 10th. I never start off the show with the date, so I don't know why, but today we have our guest, Andrei. How are you today?
I am doing well. I'm doing very well.
Nice. So Andrei and I are in the same physics class, so we are going to be discussing physics today. And Sebastian, my co-host, is here as always.
As always, and I am not in their physics class.
Yeah.
I do have yet to take a physics class through actual school, but I was taking things not specifically physics, like just at a general level, but around the topic at, outside programs. But I do feel like you guys are largely going to be taking the lead on this, and I'll maybe posit how it, connects to quantum mechanics or any other connections that I can make.
Yeah.
Cool.
There we go.
Yeah, it's really interesting. So a lot of this whole season is centered around space and a lot of sort of futuristic technologies. But me and Sebastian sort of realized a lot of these have strong foundations in physics. So you need to sort of understand how the universe works in order to understand the possibilities of these future technologies. But before we get into that, we will start with the plugs. So visit the Gravity Max website at gravitymaxmedia.com. It is a website where we put previews to my books and Sebastian's books.
They're coming. They're coming.
Yeah, they're coming. Coming soon, Sebastian's books. And then also there's a news tab. The most recent article is from June. You might want to check it out. But and then there's also the Gravity Max social media, Instagram, Twitter, Facebook, and Patreon. Links in the description to everything. Also, follow Sebastian on social media, Instagram, Twitter, and of course his YouTube channel, 128 Seconds, where he discusses scientific, historical, a lot of different topics and covers them in 128 seconds to sort of provide a quicker version of what we do here in 2 hours on stream. So
I've been on a break up until now.
Okay.
So you guys should expect a video this Wednesday.
Nice.
Wow.
Nice.
Breaking.
Exciting.
Only here.
Dude, the political compass video is still blowing up.
It's
not blowing up, but it is doing so much better than I ever expected it to do. I think we're around 600 views on it. It is crazy, considering that that's kind of the halfway mark of my channel. So I was still using the default Windows video editor to make that video. And practically a broken microphone.
Ooh.
Because I didn't have my audio editing finesse yet. I'd taken a class, but my finesse definitely wasn't there. I've also just been horrible with slides. This is what my channel looks like. That's the logo.
Nice.
But
I will also have a video out on, speaking of videos, on January 15th. And the way that I actually know that is because it's also an assignment for my astronomy class is to make a 10-minute video. So I decided, wait a minute, I can multitask here.
There you go.
Oh, and then also check out my second channel that I started in January called Govern Max. It's about sort of legislation and stuff.
Did you put a plug slide in for that or not?
I haven't.
Right.
But just check it out. The link is not in the description, unfortunately. But if you go to my channel and you go to the tab that says channels, where I feature all the other people's channels, that's where it is. You can also just look it up. There's one video on it right now about the new Congress that was sworn in on January 3rd. And once they start passing legislation, or someone does, once Biden does an executive order, or the Supreme Court says something, then it'll be there. But right now there's only one video, but still check it out. So then A Bottled Up Flame is my second book. Link in the description. It is the sequel to the first one, A Truly Dead Rock. You can get it on Amazon. Very cool.
Very good. All right, the rules, and again we are covering ourselves again. If I can kind of.
Oh yes.
No, I'm going the other way here.
I'm not even gonna try.
There we go. Haha.
Yeah, very
Someone
nice.
take a screenshot of that. That has got to be terrifying. I mean, I'm looking at the preview, so I know it is terrifying.
Uh-huh.
But yeah, like Max was saying, a lot of the topics, pretty much all of the topics we're going to cover this stream, in this season of this stream, you do need to have some knowledge of physics, or if you understand, or if we comment on a specific aspect of physics, you can call back to this video and watch us talk about that specific, law or principle. Because when we're talking about these other topics, we're not going to go in depth about the specific physics necessarily behind them at their base level, which is kind of what we're given here. So this is more of a reference point.
Yeah, exactly. So this is sort of just about like the rules of the universe.
Yeah.
The universe is like, I don't know, analogy. But this is just like the rules, the coding, like this is how it operates. So it's sort of important because it helps you understand what is and isn't possible in terms of technology, because there are a lot of theorized technologies, and you may wonder about them, like how do we know that this is possible? Well, we know that it is possible because it is within known physics and it like operates on physical laws. It's just that we don't have, say, the material or like the resources, the energy to actually get it done right now. So it's sort of cool to know a bit of physics. But yeah, so shall we get started?
We shall.
Sure.
All right. Astrodynamics, also known as orbital mechanics, but I think astrodynamics sounds cooler, and they are interchangeable, practically. I mean, they probably aren't exactly interchangeable because that's why we have two different words. But for all intents and purposes,
for the level that we're going into it,
yeah, it's only not interchangeable to like an expert in the field that will get pissed off at you if you say they are interchangeable. That's sort of how like
and the
everything
astrophysicists,
Yeah,
click off
exactly.
this video.
Yes.
It's gonna annoy you.
To all of our astrophysicist fans,
Yeah, exactly.
we apologize.
Yeah, or yell at us in chat. Actually,
Yeah.
get that good engagement.
Oh, I should get
up.
my social media desk up. What am I doing?
Yeah,
I'm all over the place.
But yeah, so astrodynamics. This is just how things move in the presence of a gravitational field. How two bodies interact with each other in a gravitational field, or three. But three is a lot harder to predict, and we'll explain that in a little bit. So yeah, let's just start with a very simple thing: Kepler's laws of planetary motion. So Kepler, he had a friend named Tycho Brahe, and Tycho Brahe took a lot of observational data over the course of like 20 years.
Don't you mean
of
Tycho
all the planets?
Bruh?
No way. It is not pronounced Tycho Bruh.
Bruh.
I'm sorry. There is no way it's pronounced Tycho Bruh.
I think you mean Tycho Bruh.
Okay, so Tycho took a lot of observational data over like 20 years. However, he never theorized. He was just like, I just like doing the astronomy. Like he wasn't a theorist. So then when he died, he gave it all to Kepler, and Kepler used it to develop these three laws of planetary motion. So the first one is that, and this just applies to anything orbiting another thing. So this also applies to the moon orbiting the Earth, a planet orbiting a distant star. It's just planetary motion was the one that was most easy to observe. But anyway, so the laws state that planets orbit in elliptical orbits around the sun, with the sun being one focus of the ellipse. And that is sort of different to previous conceptions. People thought the planets would be in circular orbits, and they can be in circular orbits, and they're actually very close to circular orbits, but they are actually elliptical. The second law is that, so it's kind of confusing, but an orbiting object will, if you draw a line between the object and the sun, then that line will sweep out equal areas in equal amounts of time. And practically what this means is that when an object is closer to the sun, it is moving with more speed because the line between it and the sun is shorter. So to sweep out an equal area, it has to go a longer distance in an equal amount of time. And that's just, how speed works. And then the third law is that the semi-major axis, which is the average distance that the planet is from the sun, the cube of that, let me see, it's the cube of the semi-major axis is proportional to the square of the time it takes for the planet to make one full orbit. So those are the three laws, and they apply to everything. This was before Newton's laws of gravity. So this was just like figured out even before gravity was determined to be a thing.
If you call back to the game show, Max asked me to just use Kepler's third law, and I didn't have it on hand, but now I do. So,
yep.
Watch out.
It wasn't shorthand knowledge.
Yeah, exactly. But yeah, so some interesting things with this, I guess, are just that an object will speed up as it gets closer to, the center of mass.
Yeah.
And it's predictable in how it does it. I think you could actually use like integrals and calculus to determine like the position of a planet over time. But yeah.
In an astrophysics class, do you think that this would be like one of the first things taught?
Oh, this is like
probably.
This is probably astrophysics 101, other than just like gravity.
Yeah, exactly. Because this is very like foundational. But like where this might be important is if you think of just like satellites. If we're talking about satellites or just various structures, is that they will speed up when they get closer to an object and then slow down as they're farther away. So yeah.
There you go.
Cool. All right, next we've got orbital velocity. So orbital.
I was going to say in the orbital velocity, as we can see here, we have the radius down in the bottom, so it's very easy to see how when you have smaller radiuses, much higher velocities. So if you just want like a single equation that kind of proves that point, then there you go. It's the first one there.
Yes, that makes it very simple. Is that objects that are closer, that have smaller orbits, will move faster, whereas objects with wider orbits will move slower. So the two equations here, the first one is orbital velocity for an object on a circular orbit, which is the perfect orbit. It's the idealized orbit, eccentricity of 0, but no actual natural body follows it. But it gives you a sort of general idea for things that are close. G represents the gravitational constant, and m represents the mass of a planet. So this also tells you that if you have two objects orbiting at the same distance from, a given planet, except those two planets are of different masses, the one around the more massive planet will move quicker. And so then the second equation is orbital velocity for an elliptical orbit. And so this is like a little confusing, but the A represents the semi-major axis here, and the R represents the current distance of the object, of the orbiting body from the object. So this is sort of another expression of your like equal areas and equal times thing, because as radius gets smaller, you can see that the speed will get larger because the fraction 2 over r will get larger as r gets smaller, and that causes this whole expression within the square root to get larger as r gets smaller, which causes v to get larger as r gets smaller. So this is pretty useful too, but
the first one is basically just the second one, but you say ignore all air resistance,
Yeah, exactly.
Air resistance
yeah.
is always getting ignored.
Yeah.
Yeah.
It doesn't spin. It
Um,
doesn't do this. Yeah, there you go.
well, actually, it is pretty interesting because the first one is it's I would say it's more like the square to the rectangle. You know, like
Mm.
the first one actually does follow the second one because you could represent GM over R as GM times 1 over R or GM times 2 over R minus 1 over R. And since here, this minus 1 over A is the semi-major axis, that just means that the distance is always equivalent to the semi-major axis. So this is actually, these are the same equation, technically, you know.
That's the M. Night Shyamalan twist.
That's the twist. That these two equations, like, this is just one
Guys,
solution to the equation.
They're both the butler, and they both committed.
Exactly.
So again,
yeah.
would you guys say that this would be in like 101 base astrophysics, astrodynamics?
It would have to be.
Yeah, I would say
everything else is based off of like these few things. Mm-hmm.
Yeah.
Very cool.
All right,
Very
so
nice.
The next one is orbital resonances. So this is just like an extrapolation of the last two things here, is that if we go back to Kepler's third law, we remember that the cube of the semi-major axis is equivalent to the square of the time it takes to complete one orbit. So that means that there are set distances that will create these sort of resonance like ratios. And where we see that is in the three of the 4 Galilean moons in Jupiter. Io, every time Io orbits Jupiter once, Europa has only gone around, I don't know why. Oh, this is like in a different language. I just realized. So
yeah, it's
Io,
got an
Europa,
accent.
and Ganymede. I don't know what language this is, but Jupiter is still in English, so maybe it's French.
Yeah, I was gonna
That
say
would be my
French
guess.
because of the backwards accent on the E.
Yeah. So it couldn't be Spanish. But basically, so when Ganymede goes around once, Europa has gone around twice, and Io has gone around 4 times. And again, if you were to plug their, orbital radii into, say, the V equals square root GM over R equation, you would get, corresponding speeds. And if you plugged their semi-major axes into the Kepler's third law equation, you would also get, the corresponding values. So this is just, an application of that. And you might be asking, like, wow, this is a very strange coincidence that these 3 moons are orbiting in like perfect sync with one another, right? So that's not actually a coincidence. It is due to the gravitational effects that they have on each other. Although it is minor, they do have effects on each other. And that's what I'm saying, sort of with like, it gets harder to predict when you have more than 2 objects in a system. But when you have many moons, they will tend to sort of sync up like this because, whenever, say that Europa was a little bit too far out originally, whenever Ganymede passes Europa, it might, tug on it outward a little bit, and then it's self-correcting. And you can see this a little bit with the planets of the solar system. They aren't actually in resonances. However, they do have effects on each other. And those are very tiny effects, but it's actually like, that's how they discovered Pluto, is that they noticed there were small like deviations in orbit on Neptune and Uranus. And they
as
thought,
to how they should have been?
Yeah, as to what they were supposed to be. And they thought, oh, this must mean there's another planet out there. And that planet was Pluto, which is no longer a planet. But well, the reason they thought Pluto to be a planet is that they thought it would be another gas giant, essentially, like the mass that was calculated for was very
I can see why.
massive.
I mean, you get gas giant,
Yeah.
gas
Yeah,
giant, gas
exactly.
giant, and then they're like, okay, well,
Tiny ice
and then
ball.
the
Yeah,
smallest ice
Yeah.
ball
exactly.
ever.
It was just too,
Just like
yeah,
something the size of America just floating out
Yeah.
there.
exactly. It was too, basically the problem is that it was too far away for them to make like accurate direct measurements, so they used the effects that they thought it had on Neptune and Uranus. And so the true fact was, what they later realized was that they had overestimated or underestimated, I think it was underestimated. They underestimated the mass of Neptune. So Neptune was actually more massive than they thought it was, which cleared up all the discrepancies. And the way that they figure out the mass of objects out in space is by observing the orbits of their moons.
Mhm.
So it's actually pretty hard to figure out like Venus or Mercury because they do not have moons, but we figured it out by actually sending probes there to like measure it on site. But yeah. So that's orbital resonances. You can see them, they come into play sometimes, and they can just be sort of useful. I mean, I think our GPS satellites are in like 12-hour orbits. Well, that's more resonance with rotation, so that doesn't really,
We
that's
have
just arbitrary.
some
but
chat from
yeah, let's see.
good friend Daikaiju Productions.
Yes, Daikaiju Productions says, if I break the laws, will I receive capital punishment?
Absolutely.
Yeah.
You
Yeah,
will get
I
divided
mean,
by 0.
Ooh.
yeah, that is sort of, yeah, that's the punishment. You will get divided by 0.
Andrei, have you ever broken the laws of physics? You criminal.
Well, I'm still here, so
That's fair. That's fair.
Not that I know
He's a
of.
law-abiding citizen.
yeah.
A law-abiding citizen.
There he goes.
Yeah.
And another chat from Daikaiju Productions. That
Wait,
Oh,
wait, just
let's see.
larger than this.
He says, well, if the size of the U.S., or sorry, well, if it is the size of the U.S., it must be at least as big as Texas, which is itself larger than the sun.
The true size of Texas is
the true
still
size of
unknown to
Texas
general
is
forms
still-
of science.
Yeah, it is still in dispute.
It's so large, we're still trying to figure out a way to measure it.
Yes.
Exactly.
Observable universe, not too small.
The last
Yeah.
person to try to go from San Antonio to Houston never returned.
Never, yeah, we never heard of
He's
this
still
Hats
out
off.
there.
Pay respect
Hats off to the guy who tried.
to the guy that tried to travel.
That's
between San
more of a
Antonio and
statement on just
Houston.
Texas drivers and not on
Yeah,
the size
there
of
you
the
go.
state.
Yep.
Oh my god.
Anyway, but yeah, so the resonances, they're just sort of useful to have, exact ratios.
Mhm.
It gives you, like, say that you could coordinate time between these three, like, moons if you had, like, probes, for instance, robotic probes that you sent there. They could all sort of operate. They would all probably operate on UTC, but say that you had like human colonies or something in the future, they could actually coordinate their time systems with each other based on this simple like division. They're not out of sync, which is nice because these are also tidally locked, which means that not only is their orbital period like following this ratio with each other, their rotational period also does. So a day on Io is 1/4 as long as a day on Ganymede and 1/2 as long as a day on Europa. So yeah, that's pretty cool.
Very nice. And I just want to say it's gonna be so cool when I get offered classes like this, or when I get the option to take classes like this, because it's so much more baller to like have to plug in the mass of Mars rather than some other small formula that you have to memorize. It's like, no.
Some pebble gets thrown up into the air.
Exactly. It's like,
Yes.
no, we're calculating for when, Phobos is going to smash directly into Mars or something like that. It's like,
Exactly.
screw Dave has 100 watermelons. We're talking about the future of the
Yeah.
solar system here.
Bro, let Dave do his thing, man.
Dave's just vibing.
Why does he have so many? That's the question. But yeah, so now let's go to tidal forces, because you were talking about Phobos crashing into Mars,
There you
and that
go.
would be a result of tidal forces. So tidal forces are pretty much a result of, this is like a ignore air resistance situation, I would say, is that we often think of planets and other spherical objects in space as points. We simplify them to be like point masses at their centers, but that is not accurate, obviously. So tidal forces are the result of them actually being large spheres. So you've probably had tidal forces explained before, but basically, since the moon is way over here and it's a single point pulling on the Earth, it pulls on one side of the Earth at a slightly different angle than it pulls the other side of the Earth. You can sort of see that represented in this chart, is that the top of the Earth here is pulled slightly downward compared to the bottom of the Earth, which is pulled slightly upward by the moon. And then as well, this is a smaller effect, but they both contribute to the same thing, is that the side of the Earth that is closer to the moon is pulled on by a slightly stronger
slightly
gravitational
harder
force than on the opposite side. But the main reason for this force is what I previously mentioned, which is the difference between the angles that these parts of the Earth are pulled at. And so what this does for an object such as the Earth, since we have such large oceans, is that it squeezes the oceans and then pulls them apart again, and it pushes them around and sloshes them around, and it creates high tides and low tides as the Earth rotates through this sort of differential gravitational field. And it's important to note that the Earth's crust itself also rises and falls with high and low tide, but it only does so by, say, 3 or 4 inches, whereas the ocean may do so by many feet. So you don't really notice the Earth going up and down beneath your feet.
Are you, Max, and then I'm going to redirect this question at Andrei after you're done answering. Are you for or against tides in the ocean?
For or against tides in the ocean?
For or against them? Would you rather live on a planet that does have tides, excluding all evolution? Would you rather live on a planet with tides or no tides?
I am for tides.
See, that's where you're wrong, and I'll destroy you later.
Yeah, I would also
Andrei, are you for or against?
That's where you're wrong.
You can't have a...
Andrei, you're against tides?
Yeah,
that's
no
perfect.
tides is
I'm a member of the Flat Ocean Society, and what we want to do is we want to remove the moon as...
Yeah, that's exactly it. Without tides, you can't have a moon. So that is why I am
the
in
tides
favor of
coming
tides.
in are extremely harmful to our
It's actually
beaches.
the tide pulling on the moon and not the moon pulling on the tides.
Exactly. I myself...
Well, that is interesting, because there is an aspect of that.
Well, true, yeah. If you take just Newton's third.
Yeah.
Well, yeah, it's actually causing the moon to get slightly more distant from Earth every year. And so this is interesting. So as the moon goes around the Earth rotates slower than the moon. And what that does is it causes... Or sorry, no. The Earth rotates slightly faster than the moon orbits, right? So as the Earth rotates, it tries to make the tides rotate with it, because if you are on the Earth, you are going to rotate with the Earth. However, the moon is what causes the tides, and it is slightly behind the actual tidal bulge. So this graph right here is actually slightly incorrect, because the tidal bulge would be slightly ahead of the moon's true location if the Earth were not rotating.
We have a question in chat.
Oh yes, let's see. The question, Daikaiju Production says, is this why Canada has less gravity? No. That is due to, actually, I think it's metal deposits and the crust in the mantle.
Yeah, it's what's below Canada.
Yeah. But anyway, so since the tides are slightly ahead of where the moon is constantly pulling back on the tides, and the tides are constantly pulling forward on the moon. So this adds energy to the moon's orbit and causes it to spiral outward at a rate of 1 inch every year. But this is where Phobos comes in. If the moon were closer to the Earth, so that it rotated or it went around the Earth more than once a day, the result would be the opposite. The tidal bulge would be slightly behind the location of the moon, and this would cause the tidal bulge to sap energy from the moon's orbit and slowly draw it into the Earth, where it would crash into the Earth. That is what will happen with Phobos on Mars in like 10 million years or something. But as Andrei mentioned, you've got Newton's third law, and so that means that the moon adds energy to the rotation of the tidal bulge, and as a result, it adds energy to the Earth. So as the moon pulls forward on the tidal bulge, and the tidal bulge comes into contact with the surface of the Earth, the friction transfers the momentum, and it actually it slows down the orbit of the Earth. Sorry, I was mixing that up. So the moon is increasing in energy while the Earth is decreasing in energy.
Yeah.
So the moon, since the moon is slightly behind, it is constantly pulling backward on the tidal bulge, and that is slowing down the Earth's rotation. Eventually, the Earth's rotation would be equivalent to the period of the moon's orbit, because that is what happens. That is what already happened to the moon, because this is all just a game of reciprocity, because the moon actually the Earth exerts tides on the moon as well. And the moon, when it first formed, was actually rotating, but very quickly the Earth's tides on the moon slowed the moon so that only one face is ever showing to us. That is why we have, you don't ever see the other side of the moon in the night sky. It always looks the same. And so that is called tidal locking, which many satellites are tidally locked. The satellites of Jupiter, I said, are tidally locked to Jupiter. Pluto and Charon, they are tidally locked to each other. So lots of tidal locking occurring across the solar system. But yeah.
Very nice.
Should we go to the next one?
Yes.
Yeah.
All right.
Synchronous orbits.
Yeah. Synchronous orbits.
I can read. I can read words. That's me.
Yeah. So around Earth, this would be called a geosynchronous orbit. But the reason I just said synchronous orbits is that you can also have areosynchronous orbits. Aries being the root word for Mars. So those would be Mars synchronous. And then you can have Aphrodite synchronous orbits, which would be for Venus. They use the Greek ones for some reason for their synchronous prefixes, but that is the official. You could look it up. That is actually what it's called.
Wow.
And this basically means that the orbital period of the satellite is the same as the rate of rotation of the planet beneath it. And this is useful because
satellites up. Of course.
Yeah, if you have a satellite in a geosynchronous orbit above the Earth, it will always be in the same spot in the sky relative to a spot on the ground, because that spot on the ground will be, rotating at the same rate that it is. And so they will stay in line with each other, and you don't need to have a tracking satellite dish. And yeah, this can work on other planets too. And every planet has its own geosynchronous distance, because as we said with Kepler's laws, since semi-major axis cubed is proportional to orbital period squared, every semi-major axis has a unique orbital period. It's a one-to-one function, right? So that means that there is only one semi-major axis that results in a geosynchronous orbit. And the same can be said on Mars. There is one semi-major axis that results in an areosynchronous orbit, and that is true for all the planets. And where this is useful is that if we are talking about very futuristic things, this is where you would put a space elevator, because you would want the upper end to be in orbit, but you also wouldn't want it to move relative to the surface of the Earth so that it could stay grappled, right? So,
have we gotten confirmation that space elevators will have elevator music playing on the way up?
They have to, otherwise they're not elevators. They're just weird things that go up.
Yeah, you
They
see,
have not
I'm a member of
confirmed
the
it yet.
True Elevator Society, and we are making a push to put elevator music in space elevators. Thank you.
When's the last time you've been on a normal elevator that had elevator music?
A very long
Yeah,
time
when was the
ago,
last
that
time
makes-
I've been in an elevator?
Okay, that is true, but
Like at my
basically-
dentist's office.
yeah, the point of that question is that I don't think I've actually been on an elevator with elevator music.
Oh, you
Oh,
gotta
you-
imagine
I
it, dude.
can't remember.
You gotta
I
imagine.
cannot remember an instance of that. But also, space elevators would take probably many days to climb all the way up, and I think that
No, it's a way to
that much
pass the time.
exposure. No. That much exposure to elevator music is a lethal dose. It has actually been confirmed by scientific study. If you listen to more than 2 hours and 30 minutes of elevator music, that actually has a 50% chance of causing total organ failure. So,
Oregon
so there can be no elevator music on the space elevators. That is,
Wow.
it is
Debbie
unfortunate.
Downer over here thinks that we
I'm
can't
not Debbie
handle
Downer.
some smooth jazz on the way up to low Earth orbit.
Well, you know what? Maybe the scientists of the future can figure out some chemical that makes humans more resistant to elevator music. What do you think?
More resist.
It could be done. It's the next.
It could be done.
That is why the U.S. military has a $900
Yeah,
billion
That's
budget.
DARPA. Yeah,
It's
exactly.
just so that we can. It's just all elevator music research.
Exactly. But yeah, so that's the geosynchronous orbits. Now we will get to the final topic in this section, which is Lagrange points. So as I mentioned,
Lagrange, our old enemy.
yes, Lagrange. So as I mentioned, it is very easy to predict what two objects will do when under the influence of their mutual gravitational fields. But as soon as you add a third object of comparable mass, it's all just thrown out the window. It is just utter confusion and chaos, like literally chaos, actually. It's used as a demonstration of chaos theory. So, yeah. But if you have an object, if you have two objects that are similar in mass, like a planet and a star, and then you have a third object that is much, much smaller, like a satellite, there are 5 distinct points in space where you can put that object and it will stay put relative to the orbiting system. And those are called the Lagrange points. So they are simply L1, L2, L3, L4, and L5. And so what this means is the L1 point is between the Earth and the Sun. So if you're conceptualizing this, think the Earth is pulling back on the satellite just as much as the Sun is pulling forward on it. So it is balanced between these two objects. The L2 point is so the L1 point, that was actually a simplified explanation, but the L2 point is a bit more complicated if you think about it. Basically what it is we keep self-referencing here, but if we go back to Kepler's laws again, right? Or if we go to the orbital velocity equations, okay? When mass increases and the radius stays the same, then an object will move at a faster speed. So the L2 point object has both the Earth and the Sun pulling on it, which is greater in mass than just the Sun. So if an object were at this distance from the Sun, but there was not the Earth there, it would actually move slower. But since the Earth is there, its gravitational influence speeds up the L2 point object. And the opposite occurs for the L1 point object. Because the Earth is pulling in the opposite direction, it is actually reducing the effective mass of the Sun because, it is not, its gravitational influence is being counteracted partially. So that causes the L1 point to move at a slower speed. And then you've got the L3 point, which is, again, the combined gravitation of the Earth and the Sun causes the L3 point object to behave slightly differently. L4 and L5 are basically like equilateral triangles with the Earth and Sun, which means that the Earth and Sun are an equal distance away from this object, which means that the object is co-orbiting the actual center of mass of the system of the Earth and the Sun. It's kind of complicated, but basically these points will stay in place as this whole system rotates. However, there are a few caveats here. And the first one is that the L1 point, the L2 point, and the L3 point are unstable. So when you put a satellite there and you just leave it there and don't do anything to it, it will eventually fall out of place and either drift into a heliocentric orbit or into a geocentric orbit. And it will get misaligned, which is unfortunate because the whole point of putting it there is so that it stays in one spot. But you can see how this happens by looking at these sort of gravity wells. Like, doesn't it look like the L1 point is like precariously balanced between two pits,
Yeah.
That is sort of how it is. And it's the same with the L2 point and L3 point because they are not self-correcting. So if the L1 point object gets accidentally shoved a little closer to Earth, since it is a little closer to Earth, it causes it to have to feel more of a gravitational force from Earth, which pulls it more off course, and that is a positive feedback loop, although it has negative results. It's funny, when people say positive and negative feedback loop, they usually mean whether or not it's a good thing. It perplexes me. But people will say, oh, that's a negative feedback loop. And I'm like, no. It's bad because it's a positive feedback loop. Because
something's actually showing up, therefore positive.
Well, yeah, exactly. Say with melting of the ice sheets, for instance, this is a very common one, is that since the ice sheets are very reflective, when they melt, the result is that the Earth will absorb more heat, which will result in more melting of ice sheets, and that is a positive feedback loop. But so often I hear people refer to that as a negative feedback loop, and I'm like, yes, it is a bad thing, but that is not what positive and negative means here. So positive means that a small change will result in...
You heard it here first, folks. Gravity Max believes that the melting of the ice sheets is a positive thing. We got you in 1080p.
Anyways, so the point is, a positive feedback loop is when a small change results in another change that results in another change, and it builds on itself exponentially. So then the L4 and L5 points are actually somewhat self-correcting. So they are in a negative feedback loop, because when they get a little bit off course, the result is for the combined forces to bring them back into the proper location. So that's a negative feedback loop. But this doesn't mean that you can't put things at the L1, 2, or 3 points. It just means that whatever you put there needs to have correction, like rockets. It needs to have proper station keeping, which the ISS, for instance, has station keeping because since it's 400 miles above the Earth and there is no true end of the atmosphere, it just gets less and less dense. There is slight drag on the International Space Station, which causes it to lose energy in its orbit, and it decreases its orbital altitude slightly, so it has to every once in a while correct by burning some fuel and entering a higher orbit. But yeah, so you can put stuff here. We already have put stuff here. For instance, we have a telescope that is just constantly observing the sun at the L1 point, which is a pretty useful thing to have, because you can always see the sun from that point of view. We also have a telescope that is pointed at the Earth from the L1 point, and that's also useful because it just shows you the daytime side of the Earth. I'm not sure if we have telescopes at the L2 point, but if you were to put a telescope at the L2 point, you could essentially use the Earth as a way to block out the sun, which would be pretty useful. And yeah. Actually, the Earth might be too small for that, so never mind. But yeah, that is the Lagrange points. There's a ton of different applications for these. And there are actually natural objects in some of them, because since the L4 and L5 points are self-correcting, they actually attract objects, and Jupiter and all the other gas giants have a lot of just asteroids that are trailing ahead or behind them in their orbit at the L4 and L5 point. For Jupiter, they're called the Trojans. Isn't that fun?
Nice.
The Trojan asteroids.
Wow.
But yeah, so that is the astrodynamics section. So now we've got some just pure physics stuff that we're going to talk about.
Yeah, physics, the original science.
The original science.
The original
All
science.
of
It came a little after the cavemen were like, all right, what kills us, what doesn't. That was the first science.
Yeah.
They were like,
Medicine.
all right, so Grog went and he ate this blue flower.
Yeah.
Now Grog no move must mean blue flower not very
Dead.
tasty. You know, and that was the first science.
Yes.
And then the second came from how hard do I, swing this stick to a.
Yes.
Anyway.
Yeah, exactly.
And then the next one was computer science. So
Yeah,
anyways,
yep.
getting into
Yes.
after a solid burn on computer science majors, we move on to physics.
Wow.
Yes. So let's start with Newton's laws.
Newton's
So-
laws.
Just like Kepler, Newton decided to make 3 laws, which is nice. I feel like there's something about 3.
A rule of threes here.
Yeah, it's like comedy.
He figured out
but
more
yeah,
things,
so-
but he just wanted to keep it at 3. So this is
Yeah.
what he let us
No,
have.
like he could have probably like combined some of these.
Mm.
You know what I mean? Or he could have split them up. Like, there's no reason he couldn't have said first law, objects at rest remain at rest, and then second law, objects in motion remain in motion. But anyway,
Yeah.
so the first law is objects at rest remain at rest, and objects in motion stay in motion. This is essentially inertia, and the principle is that you must provide an external force to cause an object to change course. Otherwise, it will just travel in a straight line or just stay put. So then the second law is how you calculate force, and that is force is equal to mass times acceleration. So
Full
this
Metal
also-
Alchemist.
FMA, yeah. So basically, this tells you that if you want to cause a 1 meter per second acceleration to a 1 kilogram object, you need to provide 1 Newton of force. It's just, it's that simple. And then the third law is for every action, there is an equal and opposite reaction. And this is, I think it's a pretty interesting law because you may not think it to be true, like you may not see it. It's not like intuitive to life on Earth. And that is because on Earth, there are surfaces and there is air that results in friction. And friction sort of seems to come from nowhere. Like, it's not very obvious what's going on when there's friction, you know what I mean? So when you say, and actually that's sort of makes the first law non-intuitive as well, because you may, if you slide your phone across the table, it'll come to a stop. And that is because a force is acting on it, that's the force of friction. It's just that it's sort of non-obvious because you think, well, it's just moving on a surface, right? But in space, I would say Newton's laws of motion are like magnified because
it's their playground because you have a lot less wind resistance.
Yep.
Yes. We
Yeah,
have finally eliminated air resistance.
Air resistance.
That's exactly it. Because so when I am sitting in this chair, this is sort of with the third law, and I throw this water bottle, say it's half a kilogram.
Mm-hmm.
Like if I were to throw it, nothing would happen. I would just essentially stay in place. But if you were floating in space and you threw an object that weighed half a kilogram or had a mass of half a kilogram, it would actually cause you to move backward in the opposite direction. You don't really notice that on Earth that much.
Mm-hmm.
And then, again, first law type of stuff, it's it seems like sci-fi show like directors and sci-fi movie directors don't seem to understand Newton's first law, because they'll have the rocket ships like keeping their engines on while moving at a constant speed, which doesn't make sense. And if their engines stop, then the ship stops. And
yeah, they
again,
just stop moving. Yeah.
yeah, again, that is the Earth-based like false intuition, is that when you drive a car and you take your foot off the accelerator, the car eventually comes to a stop. But that is because of friction, and there is no friction in space. Negligible, at least. There's negligible friction in space. And this isn't like physics class, like ignore air resistance. This is like there is very little. It actually
it's a vacuum.
doesn't have.
There actually is no air.
In deep
We
space,
checked.
there's like 5 atoms of hydrogen per like cubic meter or something. So that's the resistance you're facing. But yeah, this is just important to. I mean, there's so many things. This sort of applies to like the rocket equation a little bit, which is the rocket equation sort of relies on like momentum a little bit, because it basically asks you how fast is your fuel being expelled from the rocket, and how much mass is there in the fuel relative to the rocket itself. Because another way to express the Newton's second law of force equals mass times acceleration is that force equals change in momentum divided by time.
That's convenient.
Yeah. Well, this is actually what we did in like physics class like last week.
Yeah, I was gonna say literally last week.
Yeah, exactly. So, because basically, if you just look at the units here, right? So mass is kilograms, and then acceleration is meters per second squared. Momentum is kilograms times meters per second, because it is speed plus or speed times mass. So if you divide that by seconds again, you are squaring the seconds in the denominator. So that's another way to express the second law, and that applies to space. So that's interesting, because you have to transfer your momentum to change your speed. There's a lot of stuff like that.
Yeah. And this is like super basic stuff as well. Like,
yeah.
They taught it in 8th grade, but I
Mm-hmm.
think I knew pretty much all 3 of these. Like, I might not have memorized or known which was which, but I had a general understanding of the 3 before I walked in the 8th grade.
Yeah.
So yeah, simple stuff.
Well, yeah, it is really interesting because it is simple, like it is like the basics, like it's the foundation of physics. However, in our day-to-day lives on Earth, they are actually non-obvious. Like you have to think about them for a while to actually see where they are in your daily life. Because, the first law is saying an object in motion will stay in motion unless acted upon by an unbalanced force. You don't think of air resistance as an unbalanced force, but it is. So, yeah.
There you go. All right.
So next, we've got conservation of momentum. So yeah, I just talked about momentum, and this is basically that when 2 objects collide, the momentum is stored. And this is the same sort of thing I was talking about, like when you throw an object in space, is that you and the object are not moving at first. So when you throw an object that is 1/100th your mass, whatever speed it begins to travel at, you will travel at 1/100th that speed, because that when you multiply your mass by your speed and the object's mass by its speed, they will cancel out and remain at 0, which is where you started. So you can't add or subtract momentum to a system. That is the basic principle here.
This is like the same case of Newton's cradle, right? When you have the
exactly.
balls and you push one of them. This is also if you have like 2 objects of perfectly equal mass going at perfectly equal velocities, and then they hit each other dead on, they'll just stop.
Yeah.
Exactly. There's a lot of cool things that you can do here. There's even little projections that you can do with center of mass, which is kind of a crucial part of this all. where you will see how the center of mass in basically all of these cases will either like not move at all, or it will move at the exact same speed no matter what these objects are doing. So they could be crashing into each other at random times, but the center of mass is very much moving in a very straight line.
Yeah, that's interesting. You could have like 100 objects just sort of colliding and like just being chaotic, but the center of mass would just stay in a straight line. Because that is the conservation of momentum. Momentum will be constant all the time, which is sort of crazy.
They like to move it.
They love to move it. And
yes.
Momentum problems love to move it.
They love to move it. But yeah, again, this applies to rockets, because a rocket will have to rely on conservation of momentum, because if fuel makes up half the mass of the rocket, then when that fuel is expelled at like velocity v, the rocket will travel in the other direction at velocity v. It's actually not as simple as that, because for part of your journey, for part of your journey, the problem is that you are accelerating the rocket and the unused fuel. You know what I mean? So when you have a full fuel tank and you accelerate, you aren't accelerating as much as when you have an empty fuel tank. So
you kind of accelerate even faster as you go.
Yeah, exactly, as you run out. So yeah, this applies to rocketry. This applies to like the active support structures, which we've talked about a few times, but that is basically just a transfer of momentum. And the principle here is if you have an upward stream of particles that is then redirected downward in like a very tall tower, that tower can actually be much taller than it would be on its own, just with its own, tensile strength and support. Because when you redirect the stream of particles, its momentum has just transferred from being upward to being downward, which means that to conserve momentum, you have to transfer it into the building itself. And now the building gets some upward like momentum. But of course, it's in a gravitational field, so there's acceleration, and the building doesn't just start moving upward.
Yeah, I remember.
But it supports it against collapse.
When we were talking about these in 8th grade, and Jam was in my 8th grade science class, so he can attest to this. But one day they asked us the question, what would happen if all of Newton's laws went away? And
I remember that.
We had to come up with like everything that would happen.
You would just die.
You would like no clip through like reality. Everything
honestly,
would just you would find yourself in the back rooms, and there would be no way out.
It would just be very buggy.
Yeah.
Simulation.
But anyways.
But yeah. So next we've got conservation of energy. The universe relies on a lot of conservation, I will say.
Yes.
There's like in particle physics, you've got like conservation of charge, conservation of lepton number, quark number, weird things like that. But here, what this means is that different types of energy can be converted into one another, but energy can never be destroyed. So here you see there's a ball rolling down a path, and as it enters a divot, it speeds up, but then when it exits the divot again, it slows down. And that is because there are two types of energy here. There is gravitational potential energy, and there is kinetic energy. So
Hold
gravitational
on.
Yeah, what's up?
I slammed my hand down on my keyboard by accident, and it just went black. So our cameras are still here. I just sent us into into
the dark realm.
The dark realm. God, it didn't even make a new slide. It just like tabbed out. I was stretching and I put my hand down and it hit like the 0 and I guess like the delete key. And it just went into another realm. But we're good.
Great.
We're back.
Okay. We're back. But yeah, so gravitational potential energy.
I'm gonna watch that replay. That's hysterical.
Yeah, gravitational potential energy increases with height. and then kinetic energy increases with speed. So that is why, as the object gets lower in the gravitational field, its potential energy gets lower, and in kind, the kinetic energy has to get higher because energy must be conserved. And then when it gets out of the divot again, it will return to its original state. So this is very useful for like doing calculations because on the next slide, we'll show you how to calculate kinetic energy, but like gravitational potential energy can be calculated by the mass of the object times the like g, which is acceleration due to gravity, and then the times again the height of the object. And so that's just useful because if you know that you start with some amount of gravitational potential energy and end with a lower amount, and then you also know that you started with some amount of kinetic energy and ended with a higher amount, you can precisely calculate how much higher that new amount must be. And as a result, you can calculate the new speed of the object because the equation for kinetic energy involves the speed of the object. Or the velocity, but it actually doesn't matter in this instance. Usually it does matter whether you're talking about velocity or speed, but for kinetic energy, it actually does not matter because it's velocity squared, which is always positive. So speed squared is also always positive.
Functionally, this just like the conservation of energy just means that when you start doing problems, you can skip a lot of it if you just know things like, you know, starting energies and ending energy, because you know ultimately no matter what happens, they have to be the same.
Yep, exactly. But yeah, it's also useful, again, like applications and stuff, is that for objects that are in orbit, higher orbits have more gravitational potential energy, but since they have lower speeds, they also have less kinetic energy. But I think the amount of gravitational potential energy in a higher orbit is actually greater than the amount of kinetic energy, like it is lower than, you know what I'm saying?
So
you have to add energy.
Yeah, we've been talking about the conservation of momentum and the conservation of energy. I would like to hear your opinions on whether you are for or against this conservation.
Well, I think conservation efforts around the world and around the universe are very important.
Oh, that's very nice. I'm actually from the conservative party of the universe, and I wanted to hear
what
you wanted to join us.
Wait, so I'm not sure if that means you are pro or against the conservation.
We're pro-conservation. That's why the conservative party of the universe.
All right, so that's wonderful.
Conservation of energy, yeah. Not to be confused with the redistribution party of the universe that redistributes all of the energy.
Uh-oh. The entropy party.
Yeah.
Entropy party.
Yes, energy must not be concentrated in the hands of a few atoms. It must be distributed equally amongst the universe.
The means of production must be in the hands of the heavenly bodies.
Exactly. The entropy party will end up winning, unfortunately.
At the end, yeah.
Eventually.
Yep.
But our fight will be legendary.
It will be.
Yes, exactly.
Right.
Anyway, so that's conservation of energy.
And the slides just do not want to switch. There we go.
Okay. Next we got kinetic energy. So kinetic energy is equal to half of mv squared. And this is just useful, again, for like solving, but it also is useful for thinking about objects moving in space. So when an object is in orbit, it is moving at around 8,000 meters per second if it is in low Earth orbit, which means that in a head-to-head collision between two objects, there will be a lot of energy involved, but people seem to underestimate the amount of energy that is, because kinetic energy equal to half of the mass times the velocity squared. And that squared part is important.
Very important. This is what this is what people mean by speed kills when we're driving.
Yes, exactly, because while it may not seem like it, if you like, crash into a wall at 30 miles per hour, right? That collision involves 1/4 the amount of energy as a collision as at 60 miles per hour.
Yeah.
And
Not
yeah.
Not 1/2, 1/4. Yeah. There you go.
Yep. And so that is like ramped up to a crazy degree in space, because at 8,000 meters per second, an object the size, like literally a fleck of paint, can cause like a massive like dent to form.
Yeah.
In
This
object.
is why guns work. Like the mass is incredibly tiny, but because the velocity is so large, it's able to, do what guns do.
Yes, exactly. So you got to think of those 8,000 meters per second squared, which is much more. That's like 16 million.
Yeah.
Meters squared per second squared. So then you have to multiply it by other stuff to get something meaningful, but still, that is a lot. And this ramps up even further when we talk about, say, like planetary travel, because those require pretty fast speeds. So like if a grain of dust, impacts your ship, you got to worry about that. And then interstellar travel would presumably require even faster speeds, possibly even relativistic speeds. And compared to just low Earth orbit orbital velocity of 8,000 meters per second, which seems monumental compared to just things on Earth, relativistic velocities, say 1/3 the speed of light, would be 100 million meters per second. So we've just gone from 8,000 to 100 million meters per second, which means, and as monumental as that difference alone is, that's about a factor of like, it's a little more than a factor of 10,000 right there. 100, like, yeah, 8,000 to 100 million. So you got to square that factor, and that factor is then like, 100 million again. So an object colliding with you at 1/3 of light speed will have 100 million times the energy as an object colliding with you at orbital velocities, which is already disastrous. We've already had satellites destroyed. You may recall there's like a hole, like there was once like a hole in the ISS. They patched it up. It was like all fine, but it was still like concerning. And so when you are engaging in interstellar travel, you have to make these considerations, because like every atom that collides with your ship is providing such an explosion to that ship. It is like ridiculous. And what this also means is that an effective weapon in space might be to just get an object going really fast, like no explosive, you don't need no nukes, no chemical explosions, just an object moving very quickly.
Yeah,
like,
that was
can be destructive.
Question on the last game show.
Exactly.
What were those things
called? It was called a kinetic bombardment weapon. But that only relies on like orbital velocity type stuff. There's something called, I think it might be like Isaac Arthur, if you know that guy. I think he coined this term. He's like the leading futurist YouTuber. He called it a relativistic kill missile, which is pretty apt. Because you could like essentially take, an object that's like the size of like a 18-wheeler, accelerate it up to very close to light speed, and just hurl it at a planet. That would be nuclear, like that would be larger than a nuclear explosion. It would be devastating. So yeah, that is the power of kinetic energy. And that is why in space, we will have to be very careful, because space is so big, which means that if you want to get from place to place practically, you do need to go very quickly. But as a result of that, we are going to have a lot of like safety regulations will be necessary to prevent that speed being used dangerously. I mean, think about all the security around simple airplanes at this point. and they really aren't that fast in the grand scheme of things. So
Really not.
yeah, there's going to be mega TSA in the future. But yeah, so that's the end for our physics section. And we should have called that the Newtonian physics section, because what we're about to go into is called relativity, which is really just the Einsteinian physics section.
Mhm.
But yeah, so relativity. So first, hats off to the general. Hats off to the general.
Hats off.
This is general relativity. This is Einstein's theory that, basically describes gravity as not a force, but a curvature in space and time itself, which is apt but also confusing and hard to work with like when trying to do math. So it's easier to just think of it as Newtonian, but it is actually Einsteinian. So yeah, what's up here?
We've talked about general relativity a lot, especially when we get into science fiction stuff, because a lot of science fiction you will see is actually related to general relativity. Most notably, like time travel is probably like the most common thing, and that relates to general relativity and like sci-fi stuff. But we've talked about that like quite a bit.
Yeah.
But that
we've talked about. Yeah, sorry, we've talked about general relativity.
We have a entire game show dedicated to general relativity. So.
Yep.
Oh, I forgot to throw them in. I
have a relativity
I said
episode
I was going to
too.
throw them in.
Oh yeah. We have a guy.
Yeah.
It's a joke because
Here,
we have the quantum mechanic.
I will put them in.
And then there is general relativity. So yeah, it's funny. But yeah, so applications of general relativity, I mean, I think that's really what the next slides are. So I think we should just go to the next slide. So
yeah, I want to find him. There he is.
You want to find him?
I got him.
All right. Yeah, get him.
It sucks that I can't just Google general relativity.
Yeah,
and he
honestly.
Can't come up.
Yep.
All right. He. Can you paste? There he is.
There we go.
The general himself.
1, 2, 3 RF, general relativity.
Yes.
But yeah.
The watermark all over it.
Yep. So yeah, let's go to the next slide. We'll talk about some of the general's marching orders, Yep. So these are some things that the general insists upon. So first, we have the cosmic speed limit. And that is, unfortunately, when I looked up cosmic speed limit, they would only show me speed limit signs that were in miles per second, which is a horrible unit. But for the sake of the joke, of it being a speed limit, I had to make that sacrifice. So 186,000 miles per second, which I will add, I think it is a travesty that in school, this is how they introduce us to light speed. The first time I had heard the concrete, light speed was in 3rd grade. They described it as 186,000 miles per second.
Yeah, I think that was
which is unfortunate.
Too. This is America.
It's unfortunate. Yeah.
This is America.
Yeah.
Yeah, instead of, hamburgers per Walmart, we're going to use 300
Freedom Eagle.
Exactly.
We're going to use 300 million meters per second or 300,000 kilometers per second. But basically what the cosmic speed limit is just a velocity at which you cannot exceed if you are an object with mass. So no object that has mass can get to that speed. It can get very close, but it can't actually arrive at that speed. There are objects that don't have mass, primarily light, but there are other objects like gluons. I think, gluons don't have mass. All the bosons really don't have much mass. So objects that have 0 mass will travel at this precise speed. Everything else will travel at any speed less than that. So So if we just go back to the kinetic energy equation, if we think back to it, that is actually Newtonian, and you can't just keep adding energy because once you get to relativistic speeds, general relativity starts to take effect, and the actual energy of motion begins to increase much faster than the already fast half of mv squared. And actually, the amount of energy it would require to go, so the amount of energy it would require to go from 1 meter per second to 2 meters per second is so much less than it would take to go from 290 million meters per second to 290 million and 1 meters per second, because as you approach light speed, it's asymptotic and it actually approaches infinity, and that is practically why you can't reach light speed. It's not just an arbitrary thing that you'll get up to light speed and then suddenly just be like, oh, that's weird, I can't go any faster. It's that you can never get to light speed because each successive unit of increased velocity requires so much more energy. And that is because of just the relativistic effects. They make your effective mass increase to the point of infinity. And since F equals ma, right, and it also, F also equals, momentum over time, there is no way to increase the speed of an object that has infinite mass, And so as the mass gets greater and greater, it has more inertia and it gets harder to speed up. So this is all just the physics wrapping together. So yeah, that is the cosmic speed limit. There's no way to go faster. What do you think, Sebastian? Do you think it would be a good idea to try and build a cosmic Autobahn?
Yeah, absolutely. We would need the German engineering of the actual Autobahn and the German drivers of the Autobahn.
Exactly.
To do
no
it.
speed limit.
Exactly. Yep. It's just you can hop on this highway and then you floor it with your hyperdrive and you go warp 19.
Exactly.
And then finally you can make it from San Antonio to Houston going at warp 19.
Yeah. That would be pretty interesting, actually, if we develop some sort of warp drive-esque technology that allows you to sort of skirt around this speed limit. I just find it an entertaining concept if you had to dedicate a region of space to it, and you didn't want to make all of space into this sort of lawless type of zone because it would mess things up with physics. Maybe it you're able to sort of make all the physics weird. So sort of societies in the future, once they figure out how to do it, they would set up an Autobahn, and they might call it that. I think that would be entertaining. Just from
That's
a story.
BMW's next project.
Exactly. Just from a story writing perspective. A lot of the stuff that I think on here, a lot of futuristic stuff is not actually practical. There's a much easier way to do it, assuming you did have the technology, you know what I'm saying? But for the sake of story structure, it is very appealing. And since I'm also, a sci-fi author, I've got, that sort of appealing aesthetic quality. I think about that all the time. So yeah. So that's the cosmic speed limit.
There you go.
So next,
Schwarzschild Radius.
Yeah, Schwarzschild Radius.
Or is that how you say it?
I don't know. It's German, so.
Yeah, I think I called it Schwarzschild on my black holes video. I hope I don't get doxxed by the Germans.
Oh no.
Yeah, I guess it would be Schwarzschild, right? Because you've got the SCH. I guess that's how it would be. That would be my guess.
I don't know.
But anyway, this is sort of like the cosmic speed limit, but it's like a cosmic mass limit or a cosmic density limit. It basically describes a minimum radius for creating a black hole, or I guess a maximum radius, actually. So you have to cram all this stuff into a space smaller than the Schwarzschild radius in order to create a black hole. And the equation for that is 2 times the gravitational constant divided by the speed of light squared, and then that fraction, that constant fraction times the mass. And so this has an interesting effect, actually, because when you double the radius of an object, the mass of that object, assuming density stays the same, increases by a factor of 8, because we are in 3 dimensions, and the result of that is that when you increase the size of something, it doesn't just increase in length, but it increases in height and in width. And the equation for the volume of a sphere is 4/3 pi r cubed, I believe. And so that has the effect of meaning that any density, any object of any density, will eventually become a black hole if you make it large enough, which is very counterintuitive. It doesn't make a lot of sense, but it is true.
I don't know, I find it kind of uplifting. If you're ever feeling down, you could just be like, hey, if I implode right now, all of y'all are done.
Yeah, okay.
You guys best keep me from imploding.
Exactly. Well, yeah, it's just a really interesting thing, because you can accidentally create a black hole if you just have too many things next to each other.
Oh wow.
That's the problem here, because any function where you have a straight line and a cubic, the cubic will eventually intersect with the line. Mm-hmm. And that is what you're looking at here, because mass will naturally increase with the cube of radius. And so since mass is increasing, that fast, whereas the actual radius is only increasing linearly with mass, it creates problems. Because say that you have an object of mass 1 and radius 1, and then you increase it to have a radius of 2. It will now have a radius of 8. And that means that it might be within the Schwarzschild radius, because that mass of 8, times this constant might be greater than the radius of 2. Whereas before, a mass of 1 times this constant would not be less than, or whatever I was saying, than a radius of 1. And so basically what this means is that if you just have enough space stations, right? If you are a crazy intergalactic ancient civilization, right? And you just accidentally have too many habitation pods next to each other, it will create a black hole. You will just be within the event horizon of a black hole. And so that's with any density. Again, the density of air, a cloud of air large enough will be within its own Schwarzschild radius, because of this principle I'm talking about, this simple mathematical principle. And so that means that there's a maximum, there's a density limit to space. You have to keep it so sparse so that it doesn't become a black hole. And this is pretty weird to me, because it feels like it's proof that the universe is not infinite, right? Because otherwise we would be inside a black hole.
True.
IDK. Maybe we are in a black hole. Because it's possible, because this could be a pocket dimension, you know what I'm saying? It could be a pocket universe. But that is just beyond the scope of this discussion. There is no way to tell.
Would
it's
you
an
be
unfalsifiable
would
claim.
You be for or against existing in a pocket dimension?
If we could create our own pocket dimensions based on this revelation, then yes, I would be.
That's fantastic. I'm actually a recruiter from the University of Pocket Dimensions, and I would like to give you a pamphlet.
Oh, wow. Thank you. Anyways, that's the Schwarzschild radius. Oh, you can also do stuff with energy. This is called a Kugelblitz black hole. And we'll talk about E equals mc squared, but if you put enough energy in a very tight volume such that the equivalent of that energy is enough mass to create a black hole, then it is theorized that you could create a black hole out of energy. It hasn't been tested yet, and based on stuff with like the 4 fundamental forces like merge together at too high a temperature, it might be that you actually can't create a Kugelblitz black hole because the laws of physics would be different at such high temperatures with such a high energy density. Yet to be tested, but because we just do not have the sheer amount of energy to do that, or the focusing power. I suppose we could do it with the amount of energy we have today. We would just need to be able to focus it in a very tight beam, which we cannot do yet. So yeah, that's that. So next, time dilation. So time dilation has 2 main sources. They are
analog and digital.
Yes, they are speed and mass. So this is just general relativity 101. I mean, I bet we've talked about this before.
Yeah, we've talked about this so much.
Yeah.
Go ahead if you want.
But yeah, if you are going on a interstellar trip and you are operating within known physics and going very close to light speed, and you have, sufficient shielding so that a single atom doesn't nuke your ship, then you will experience the results of time dilation. And what that means is that depending on how fast you go, you will experience time much, much slower. So you could have a trip that crosses the entire Milky Way galaxy, which would be 100,000 light years, and so would take approximately 100,000 years if you're going very close to light speed. But from your perspective, it could take, 10,000 years or 1,000, or, it could take a single second. It just depends on how fast you are truly going. And this would create some interesting things because it would cause people to age differently. But this is also true of getting close to a black hole. So say that there are, we have a few very large, black holes. There's a supermassive black hole at the center of the galaxy, and then there's a ton of other supernova stellar remnant black holes just dotted around the galaxy. And say that we find them useful for some reason, right? So we build factories there or something like that, we build stations around the black holes, and we need people to operate them. Or if we have people frequently going on interstellar trips, then the result of that will be people aging at different rates. And that would be very fascinating because, you could have people could, it would be so weird, because you could have, say, 30-year-old parents, parents that are 30 years older than their child, right? But then their child, gets a, black hole major, and they go and work at the black hole station doing research and stuff. Or actually, wait, the other way around, right? So the parents have, one of the parents, say, works in not in, but at, around black holes. Then because of the time dilation, you could have that parent aging less than the child, so that eventually the child is older than the parent, biologically speaking, which would just be very confusing. And everyone would be like, what is going on? What is this? Everyone would be confused. It would cause much confusion. But it is still there. Also, if you're it's also interesting because it's say that you didn't like the way the world was or something like that, you could just hop 10 years into the future. Yeah, imagine. And so essentially you could be oh, you don't like the 80s? Just skip the 80s. Something like that. Who would skip the 80s?
There were some bad things reflected.
Yeah, that's true.
But for the music scene,
but then you would be stuck in the 90s. If you had just come out of the 70s, why would you skip the 80s? Comparatively,
Yeah. I think 80s is probably the one of the better ones, I would say.
Yeah.
The epitome.
Yeah, you've got these cultural zeitgeists. It's funny, there shall no longer, I think, there won't be a cultural zeitgeist anymore because of the internet. Because not everyone's watching the same movies. There's no unified pop culture now. Everyone has their own sub communities, which is just fascinating. So no one can I mean, they still can and probably will, but it'll be a lot harder to nostalgically like wax about like, oh yes, the 2010s. However, the 2020s might have a zeitgeist just based on the whole pandemic situation. So there you go. But that's not something you want to be nostalgic for. So
Remember when
not
we
very.
all stayed
We're
inside
stuck
for a
inside.
year?
Yeah.
Wasn't that a goddamn nightmare?
Interesting. Yeah, exactly. But yeah, so that's time dilation.
There you go.
Next, we've got E equals mc squared, one of the most famous equations ever. And it's the energy mass equivalence. So this is just interesting. It has very interesting effects. So basically, mass can be thought of as a very concentrated form of energy because if you multiply the amount of mass you have by the speed of light squared, it results in energy, which it's just fascinating because this basically uses just SI units. So kilograms times meters squared per second squared is a joule, which is the unit of energy. So this works out, you know. But so there are some interesting effects to this. One is that light itself, photons, even though they are massless, they can have momentum, which is confusing. But since photons have a lot of energy, that energy can be thought of as mass. So even though if you were to look at their momentum, which is mass times velocity, you would say, well, they have zero mass, so they have zero momentum. They do actually have momentum because of the energy. It's just very, very little momentum, and it's equivalent to the energy stored in the photon divided by the speed of light squared, but then because it's for momentum, mass times velocity, and their velocity is the speed of light, you can actually calculate the momentum of a photon based on the energy of that photon divided by the speed of light not squared. And that will actually give you the momentum of a photon. So that can be used for solar sails and light sails, which you may or may not have heard of, but it's basically using large reflective mirrors to propel small, like not massive objects to like very fast speeds. It's like sailing. It's like using the wind to move your boat. And one reason why it's very useful is because it is something that doesn't require like the rocket equation, because it doesn't have to bring its mass with it. So a ship that is relying on solar or light sailing can be solely payload, but then also sail, which is just interesting. It can go as far as it wants, is what I'm saying. It'll never have to pick up more fuel, which is very advantageous because the problem is, as I said, is that to accelerate with a full fuel tank, you are also moving your fuel with you, and it's just sort of less effective. But here, you can travel light and travel with using light, so it's very useful. But then other effects of E equals mc squared, as I said, the Kugelblitz black hole, if the energy you have in a single spot is sufficient to be sort of like the equivalent of an amount of mass that would create a black hole, you get a black hole. And yeah, I guess that's it. This is also how we have mass in the first place, because the universe started as just a ton of energy. Yeah.
There you go.
All right.
Cosmology.
Yeah, cosmology. So this is the development of the universe and what will happen to it over time. So let's start with the expanding universe. So the expanding universe is also accelerating. So our universe is the case that is most to the right. And what this means is that the size of the universe is increasing ever more rapidly, which is just strange. It's like, what is causing this? We've called it dark energy, but we only call it that because we don't actually know what it is. So we're like, it's mysterious. Like, that's what dark energy essentially means.
Then why don't
we
we,
have no
why don't
like
we call it
explanation
mysterious
for the phenomenon.
matter? The alliteration is right there. I guess it's energy, so not
but it's not matter.
but
Yeah.
That's an issue.
Like it
I'm gonna
isn't
have to
even
take that up with the
with the
head
complaints
scientist.
department.
Yeah.
Yeah, exactly. Scientists tend to be pretty bad at naming things, I will say.
Well, they either just name it after themselves, or they call it something that is just
That it
unpleasant.
isn't,
Yeah. Oh, that's
or
also
often
true.
something that it isn't.
Yeah.
Well, that's because they name it at a point at which they don't fully understand it.
Mm.
They're like, oh, this is an interesting thing. This looks promising. Let's call it X. And then years later, they find out, oh, it's actually Y. Well, we've already published like many, many, many articles about it. I guess it's staying X. But anyway, since we are in an accelerating universe, the result of that is we know how the universe will die. And that is through the heat death, which is where everything is so spread out that, you know, everything just gets very cold because all the energy has dissipated. This is when the entropy party shall have its victory. Yeah, that's what happens. So there are other possibilities, but like they're not possible because we know they're not happening. But other things that could be like in alternate universes, right? You could have a universe that decelerates and turns around and then falls back in on itself in what's called a big crunch, which would also kind of suck. It would be like everything would, you know, slam together and get very hot. And then there's also what's known as the steady state universe, which is what scientists believed it to be before we figured out it's actually accelerating outwards. And that is, we thought it would just stay the same from past to future. It was just constant because we had no reason to believe otherwise. So yeah, but that's the accelerating universe. Yeah.
There you go.
All right. So next is stellar evolution. This is what my video will be on on Friday. So we don't have to go.
Plug.
Yeah, exactly. We don't have to go too in depth about this, but essentially, a star has a finite lifespan, and when it dies, it stimulates new star formation. However, that can only come to like a certain point, and this is just the sort of evolution of the universe. Is that eventually, after a ton of generations of stars, a lot of the hydrogen in the universe will be used up. It will be either turned into helium or other heavier elements. And once that happens, then there cannot be any more like life or energy or anything. Unless we do something about it, there is stuff we can do about it to sort of artificially generate energy, but there's no way to naturally generate energy once all the stars have used up their hydrogen fuel. So eventually, I think it's in a few trillion years or something like that, maybe many trillions of years, what will happen to the universe is it will enter this sort of dark phase where there are no more stars left. There's just stellar remnants floating around as everything drifts apart in the accelerating universe, and it's kind of depressing. But yeah.
Even the stars die.
Even the stars. So that brings me to entropy, which is what both of these things have been talking about. So entropy, the entropy party, what their goal is to take things that are ordered and make them disordered and distributed randomly. And this is just this is a law of thermodynamics, really. I think it's the second law of thermodynamics that can be briefly summarized as entropy. And it's not even like, it's more of a mathematical law, I would say, because it's just the basic fact that this ordered configuration where everything is in a neat little grid is the only ordered configuration. Whereas this random configuration, there's hundreds of different ways these like Cheerios or whatever they are can be randomly ordered. You know,
yeah,
so
I was gonna call them donuts. I was gonna say the end goal of the entropy party is to take your dozen of donuts and just throw them around.
Throw them on the floor.
And so there's just no, like, you get a chocolate next to a powder and a jelly filled next to a coconut twist. It's absolute madness, chaos in its truest form, and we must do our damnedest to stop the entropy party and its constituents.
Exactly. And its constituents.
Thank you.
Yes, he is. He is an opponent. I would say I am also. No, I do not support the entropy party.
For anyone out there that supports the entropy party, I will literally put the entropy principle to your organs and rearrange them in an order that will leave you confused.
Oh no. Do not threaten the audience.
I will threaten the audience.
Okay. Anyway, so with this combination of entropy and the accelerating universe, the result is just this state where there is no usable energy. And that is a very bad state to be in because, as I said, there is a conservation of energy. So energy must be conserved. You cannot decrease the amount of energy there is. However, to do work, it requires an energy differential. So if you have like one room with 100 joules in it and then another room with 50 joules in it, that differential can do work. But in the process of doing that work, the energy will even out to like 75 and 75, and then you can't do anything. That is basically where the universe is headed because of entropy. All of the energy will be used up. I mean, think of what a star is. A star is just a big entropy machine. There's so much energy tied up in the hydrogen atoms that gets released when they fuse together into helium, and then it streams out in a uniform sphere out into space, expanding and dissipating. That is entropy in action. And so that is the ultimate fate of the universe, unless we can figure out a way around thermodynamics.
And that also,
I
was just going to say, it puts things into perspective if you want to take it on a personal level. That's the optimistic nihilism that I think Kurzgesagt or Lemino was talking about. I forget.
Yeah, Kurzgesagt.
It was Kurzgesagt. Lemino is also fantastic.
Maybe they both were, but I don't know. I just know Kurzgesagt did.
I think that's the one that I watched. But optimistic nihilism. It's some of it is kind of dumb, but there is a good principle, and it's that if you mess up large and a lot of people see it, eventually the universe will just implode in on itself.
Yeah, the universe won't care.
The death of the universe, everything's destroyed.
Yeah.
But you can bet your butt that up until that moment, we'll remember that mistake you made, and we'll hold it to you.
Yeah, exactly. Well, it's really interesting with entropy, because I see in like sci-fi shows and stuff, people are like all hype about like, oh, we're going to figure out a way to go faster than light. And I'm like, no. If there is one law of physics you want to break, it is this one. It is the second law of thermodynamics. Like, if we could figure out how to break just one law of physics, why would you waste it on the stupid cosmic speed limit? We can wait around to get to the next star system if we don't have to deal with entropy. Like, because entropy is the reason that like you would age too much before you get there. You know what I mean? Mm-hmm. Without entropy, you'd just be fine all the way there. And you'd be like, yeah, it sucks to wait that long. However, it's whatever. So, yeah, I hate it in sci-fi shows. Well, I mean, like when they use the sort of like warp drive stuff, I'm like, why did they decide to focus on breaking that law of physics when they could have focused on breaking this one? Really, it's for story structure, and you probably can't break any law of physics because that is how physics works. But anyway, I digress, right? So finally, we have geography, hot tourist destinations.
Ooh.
Oh, yeah.
We have our tour guides, Gravity Min, and 49 seconds.
I don't know, Max. These guys are like giving me the creeps.
Yeah, they're giving me the creeps as well. I don't know who these guys are. They're just showing up.
There's a pit in my stomach.
Yeah, but they want to give us some hot tourist destinations. So this is like a
Alright.
clickbait
Yeah.
article.
Where should we go in the universe?
All right.
These guys are
So
gonna tell us.
yeah. So let's start with the solar system.
Up
Okay.
first, the solar system.
Yeah.
Personally, I live there, and I think it's pretty nice. You get some neighbors. You got the sun. Love it. Fantastic. I'm a summer type of guy, so if I could live on the sun, I would. But only at night, so that I wouldn't burn out. But
All right.
solar system, would very highly recommend it. Real estate is really good right now, considering all the unclaimed plots.
Yes.
But I definitely see a move in my future to one of the neighboring planets.
Yeah. I'd like to do that as well. But yeah, so some things of note is that our solar system has an unusually high number of planets for a solar system. Like most solar systems don't have this many planets. There are a few reasons, and one of them is that the sun is not in a binary star system, which a lot of other stars are, and that tends to lead to instability because, three-body problem, it does not work. It leads to chaos, and the planets all get flung out into space. But it's also just strange. It's rare, but it's basically the anthropic principle. We are likely here because we are in a solar system with so many planets. Not that we are lucky to be in a solar system with so many planets. It's that an Earth-like planet in a solar system with less planets probably did not develop life. That's basically the anthropic principle. But yeah, so important things. Mercury is a good source of iron.
That's confusing.
That's
yeah, exactly.
This one
iron
chemical is great if you want another chemical.
Exactly.
Yeah.
Iron and silicates. So just stuff that we can use to build massive structures like the skyscrapers and stuff that we build on Earth. That's basically what Mercury is made of. Mercury is just a giant metal mine. And it has very little value on its own as a planet. So I predict Mercury will just get disassembled. No great loss there. I think I am totally down with the disassembly of Mercury. Then we've got Venus, which could actually probably be terraformed to be pretty similar to Earth. Mars too. But Venus would actually be easier in my opinion. Well, not the terraforming, but the inhabiting first, because parts of Venus are actually more habitable than the best parts of Mars, at this moment. But we sort of have to hurry up because it's almost 7 and Sebastian has to go. The asteroid belt is also a good source of metals, and it will probably be used before Mercury is used because it has the advantage of not having a gravity well to fight against to export the materials. And then you've got the gas giants, which would likely be good sources of hydrogen and stuff if you want to do nuclear fusion if we figure that out. So a nice solar system we've got here. Pretty cool.
I'm a big fan of it. And
big fan of lots of attractions.
Yeah.
There's that Earth one. That planet's pretty pog.
It's also the deadliest planet. 100% of people have died on Earth. So
True.
Yeah, Earth is the deadliest planet.
It is.
And with that sentiment, now we go to the nearby stars.
I went to the danger zone.
So the nearby stars, a lot of them, 70 or 80%, are red dwarf stars, which are smaller than the sun. But the majority of stars we see in the sky are not that, because these red dwarf stars are so dim that if they are too far away, it is very hard to see them. However, what this means for us is that the majority of interstellar expansion would be to stars smaller than the sun, which is just very interesting. So we've got the Alpha Centauri system. That'll be interesting, 3 stars, 3 for the price of 1. Pretty cool. And there's already a planet there, so...
If you could name a star, what would you name it?
If I could name a star...
Bright Boy. I just
Bright boy.
I like it.
Maybe. No, I just have no idea.
Wow.
Wow.
Maybe because all the names I like are taken. You've got like Sirius. I like and the Canis Major constellation I think is pretty cool. The Latin, and then also that it's just related to dogs. So yeah,
Very nice.
something like that, Canis. So yeah, those are the nearby stars. They aren't too notable. That's the thing.
Ooh,
The nearby stars.
not notable. He just handed them the not notable
Yeah.
card.
Well, they don't really. It's interesting. They don't really affect the, uprising of. Why did I say uprising? But the development of life on Earth.
The
These
revolution.
stars, the revolution. I guess it actually is sort of important that we don't have any significant stars near us, because if we had a very massive star in our general vicinity, then when it would inevitably go supernova, it would blast the Earth in deadly radiation, killing all life on Earth. That would not be very pog. So it's good that all our neighbors are just very non-notable. So yeah.
Yeah, all right. Now we move on to the galaxy.
Yes.
The Milky
The
Way
Milky Way
galaxy.
So the Milky Way galaxy is interesting because it's a spiral galaxy, which is just nice. You could get an elliptical galaxy, which is pretty much just a giant cloud. Like, that's boring. The Milky Way has like spiral arms. Like, that is cool. That is what you want in a galaxy. And it's interesting because these spiral arms, as they pass through, it causes the sun to enter, denser and less dense regions of the galaxy, which actually does cause some chaos every once in a while, but it's fine, suffering for art, right? Like, you gotta deal with that. But it's a pretty big place. There's 100,000 light years, and I don't know the number, but I think it's like billions of stars maybe. So there is a lot of room to expand out here. Like, some hot tourist destinations are just like the brightest ones. It would be pretty cool to like check out like Betelgeuse before it goes like, I think it's gonna go supernova or something.
Yeah, I think so.
So
I would recommend. I've had a decent time living here. Yeah, I'd recommend it. Solid 8 out of 10.
Yeah, this galaxy.
Yeah, it could have been better. The name, not too hot about.
Milky Way.
Why is it called the Milky Way?
You don't like it?
Why is it called the Milky Way?
Because it looks like milk. Apparently,
if you're
in
drinking,
the sky,
if your milk
it looks like a band
like
of milk.
you should probably buy new
You should
milk.
probably throw it out.
Yeah.
It's sour. It's gone sour. No, that's actually.
It's gone beyond sour. It's gone stellar.
Have you ever seen? Yeah, exactly. Have you ever seen the Milky Way? I saw it on December 21st.
Oh yeah.
It kind of looks like a band of milk, I guess, but I went out to the beach. It's a very wide beach, so I was able to get very far away from any lights, and then I could actually see this. I thought it was a cloud at first, really, which is just fascinating. Just a normal Earth cloud, but it was actually a spiral arm of the plane of the galaxy. So it's pretty interesting. I would highly recommend going out on a cool, dark night and taking a look at the Milky Way galaxy.
If it's warm, you won't be able to see the Milky Way galaxy. It has to be cool.
Well, air quality, like in terms of for astronomic conditions, it is actually better. Colder air and colder, drier air, I think it is. Yeah, cool, dry air produces the least like distortions in terms of astronomy. But yeah, so anyway, that's the galaxy. Next, we've got the local group. So the local group is interesting because this is the largest group that is gravitationally bounded to us.
The lads.
Outside of the local group, everything is subject to the accelerating universe. And so it will expand and just dissipate away, recede from view. But the three largest members, the Andromeda Galaxy, the Milky Way Galaxy, and the Triangulum Galaxy, along with all these smaller galaxies, like you've got the Magellanic Clouds, they're all tight. They're very happy together, and they'll stay together. They're the lads, honestly.
Yeah.
As you so eloquently put it.
Thanks.
In about 5 billion years, the Milky Way and Andromeda Galaxy will actually undergo a merger. We're not sure if this violates antitrust law, but it's to be sorted out in court.
That's the same time when my license gets back from the DMV. Damn,
wow.
I have a conflict there.
Yeah, exactly. But yeah, so the local group it's likely going to slowly conglomerate into one large elliptical galaxy. And yeah, we'll just have to see what the Supreme Court says about this whole situation.
Yeah.
These small business galaxies are getting sort of pushed out of the market, and it's horizontal integration here.
There are some pretty anti-competitive tactics going on
yeah,
on the galactic stage.
On the galactic stage, anti-competitive practice. How are these little galaxies supposed to compete?
Yes.
But it's a controversy. You've got the conservatives and the entropists. They are in battle over this right now. But it's probably going to happen. It'll probably go through unimpeded.
Wow.
So we'll see that.
We live in a society.
We live in a society. So finally, we get to clusters, superclusters, and the universe. So on the largest scales, the universe looks like this. It's like a spongy, meshy web. Basically, the galaxy, like local group-sized objects, are part of clusters. Those clusters are part of superclusters, and those superclusters like form these like thin, like meshy column, like web things that go through the universe. And in between these like columns, they're actually called filaments. In between these filaments are very large voids that have like the occasional galaxy in them, but it's very dark. Can you imagine just going out like to the void? This is the like blackest of black space, like there is nothing out there. There's like, instead of 5 hydrogen atoms, it's probably like 1 hydrogen atom per cubic meter. It is just madness. However, if you are antisocial, it is the ideal place to go. If you want a nice secluded like cabin to get some work done, you can go out to the intergalactic void, and you'll probably have some nice peace and quiet for once, right? Get a weekend away from the kids. It's very relaxing out here in the intergalactic void. But yeah, this is all expanding, and the problem is if you want to build, say, a permanent settlement in another cluster, another supercluster, or across the filaments of the universe, you will have to say goodbye to that permanent base, because it will eventually expand with the universe and no longer be navigable. You'll no longer be able to get to it by ship, and then eventually you will no longer be able to communicate with it at all. So it's gone. It's out there. Unless, of course, we can break the laws of physics somehow. So remember that. So yeah, that's it. Final thoughts. It is almost 7. What do you guys think?
I was just gonna say how it's, and I'm probably biased because in my anatomy class the dye we used was purple, but it's kind of interesting how the picture that we have of of like the universe on a grand scale, or like the cluster, is it's very similar to skin cells if you look at it under a microscope. And I say skin cells specifically because in kind of like the pockets of darkness, those would be the individual cells, and they'd be connected to each other in a similar way through filaments. And it's really cool how like the most massive scale and one of the smallest scales kind of reflect each other.
Yes, it's the meta art,
the
meta harmony that is the universe. But Yeah, so those are the rules. We're going to have a lot of episodes about a lot of different topics that will rely on these principles and will reference our local geography in space. So this could be used as a reference point. If we'll probably say, if you missed this episode, and we're later talking about something, we can refer you to this episode. So yeah, it's a very useful episode, even for just normal physics and just like day-to-day life, I would argue, because it's good to know some physics principles. Like, say when you're driving your car and you think like, well, I got to get there, like I'm going to be late, maybe I should just speed. No, you should not, because you are actually adding so much more kinetic energy to your system than you think you are, and that can have disastrous effects. So yeah, little things like that. This is a very important episode. Physics is a very important topic.
Yes.
And yeah, I hope you all enjoyed it.
Yeah. Thank you, Andrei, for being here.
Yep. Yeah. Thank you for coming, Andrei. It was fun to talk to you.
Thank you guys.
Yeah, and I'll see you in physics class tomorrow.
Yeah.
So.
And I will be sitting in Spanish class. So thank you, everyone. Gracias for watching.
Yep.
And yeah.
Thank you all for watching. And yeah, thanks, Sebastian, for being my co-host as always. And thank you guys. Thank you, Jacob, Daikaiju Productions, for using